Okay, so we start. Welcome to this course on semiconductor optoelectronics. And let's start right away with the question of what is the subject matter of this course. As you can see, it is semiconductor optoelectronics. Semiconductor, all of us know what is a semiconductor, or do we? We will see whether we know what is a semiconductor. It's a semiconductor. Optoelectronics. Optoelectronics, probably not all of you have encountered the term earlier. Optoelectronics basically refers to phenomena and devices, study of phenomena and devices which involve interactions of optical processes with electronic processes. In other words, basically, this deals with electronic devices which involve interaction of radiation, optical radiation with electrons. That is, electronic devices which involve emission or absorption of photons. In simple terms, if you look at an LED, light emitting diode, it is basically a diode. It's an electronic diode. It's a PN junction diode, but it involves emission of light. Unlike normal rectifier diodes, it involves emission of light. Exactly like that, if you take photodetectors or photodiodes, it involves absorption of photons, absorption of light to generate photocurrent. So we basically deal with electronic devices which involve interaction of photons with the devices, photons with electronic processes. There are other terms, some synonyms which look very similar. For example, there is also a term which is electro-optics. Many times people think it is the same, electro-optics. There are also other terms like optical electronics. There are books on optical electronics. So let me just try to emphasize on the subtle difference. Optical electronics. There is also photonics. Photonics. Optoelectronics, electro-optics. I mentioned that optoelectronics refers to basically the study of electronic devices which involve emission and or absorption of photons. In electro-optics, we primarily deal with optical devices and optical systems where the properties of propagation, properties of light or propagation in the medium is affected by an applied electric field. Electro-optics refers to optical systems and optical devices. Optoelectronics refers to electronic devices and electronic systems. So this refers to optical systems and devices where the propagation properties of light or the medium is affected by an applied electric field. There are synonyms or similar terms. For example, you may have heard of acousto-optics. Acousto-optics. There is also magneto-optics. Exactly as I defined electro-optics, in acousto-optics, they also deal with optical systems or optical devices where the propagation properties of light is affected by an applied acoustic field. And in magneto-optics, The optical properties are affected by an applied magnetic field. There are many important effects. Those who are from like optoelectronics, we will have a whole course which will cover acousto-optics, magneto-optics, and electro-optics. So, magneto-optics, one of the important effects of in magneto-optics is the Faraday effect, where the polarization state, plane polarized light, the polarization state rotates due to an applied magnetic field. There are many applications of Faraday effect. Similarly, in acousto-optics, there are two important subdivisions which are Raman-Nath diffraction and Bragg diffraction with large number of applications. We will not be. Electro-optics is also very important. There are electro-optic modulators which are used for high-speed modulation. So we will not be discussing these, but I brought these just to bring about the differences or similarities between among these various titles. So our concern will be primarily optoelectronics. So we will discuss optoelectronics. There is also a couple of other terms which I had written. So let me write it again. I erased it. Optical electronics. I also would like to write another subject, that is quantum electronics. There are full courses on quantum electronics. Quantum electronics deals with devices where interaction of radiation with matter is discussed. Quantum electronics is concerned with effects, phenomena, and devices which involve interaction of radiation with matter. An important device of quantum electronics is the laser. Laser, the principle of working of a laser is explained from the theory of interaction of radiation with matter. Quantum electronics also includes nonlinear optics, lasers and nonlinear optics combined together would encompass quantum electronics. What is optical electronics? In the 1970s, all these branches, magneto-optics, electro-optics, acousto-optics, nonlinear optics, and quantum electronics were together called, that subject which discussed all these effects together was termed optical electronics. There was a very famous book by Amnon Yari of the same title, Optical Electronics. Optical electronics. Optical electronics included lasers, nonlinear optics, electro-optics, magneto-optics, acousto-optics, and most of the optical properties. Optical electronics. Then comes photonics. In the 1970s and 1980s, the developments in the optical electronics or developments in optoelectronics and optical communication was so rapid that there was a whole branch which emerged, and including optical signal processing, and the entire branch which discussed all the technologies, which included all the technologies involving light, all light wave technologies were together called photonics. So photonics, the word became popular in the 1990s. So this was in 1970s and 80s. It was called optical electronics, but from 1990 onwards, these are now all these technologies together are called photonics. So photonic encompasses all technologies which involve generation, modulation, transmission, detection of electromagnetic waves whose quantum unit is the photon, hence the name photonics. I come back to semiconductor optoelectronics. I would like to discuss the scope and contents, the context of this course. As you know that this is a core course for the program Optoelectronics and Optical Communication. So in this talk, in this first lecture, I would like to discuss the scope and context of this course. So this is the first lecture in which we will discuss the context and scope of this course, semiconductor optoelectronics. Why do we need to study semiconductor optoelectronics? Semiconductor optoelectronics came as a complete course, and in 1995 there were full books which came. I will show you a list of books shortly, and you will see that there are entire full books with the titles Semiconductor Optoelectronics. Why study semiconductor optoelectronics? If you consider, let me first take an example and illustrate. So if we consider a simple optical communication, if you take a simple optical communication link, which means there is a transmitter here, which is linked to a receiver through a medium. If I consider optical fiber communication, so this is optical communication, but if I consider optical fiber communication, if I introduce in here the word fiber, optical fiber communication, then you have a transmitter and the medium here, the medium is an optical fiber. Why do we need the medium? We will not go into those details now, but let me, if you consider a simple optical fiber communication link, so it has a transmitter, an optical fiber and a receiver. The transmitter has all the electronics, and finally there is a digital bit of stream, digital stream of bits of ones and zeros. So 1 0 1 0 0 1 0 1 and so on. It's a communication link. So if you are transmitting a voice signal, voice is first digitized. Voice is an analog signal which is digitized, and then the digitized or the coded signal is transmitted through the optical fiber. Now, The digitized signal drives a laser diode. Usually it drives a laser diode. So this digitized signal is fed to a laser diode. This is a laser diode, LD, which gives light output. If this is 101, so it will give the same way 1 0. This is 1 0 1 0 0. Is no output, and then again 1 0. So 1 0 1 0. So the laser diode is giving optical pulses. You have given electronic pulses. The bias current is modulated by the digital stream, which modulates the laser output, which means the laser output, the laser diode gives out light, no light, light, no light. So it is getting modulated. The output here is fed to an optical fiber. The light coming out from the laser diode, so there is light coming out from the laser diode, is coupled into an optical fiber, and at the receiving end you have a photodetector. A photodetector. The incident light onto the photodetector, the incident light generates a photocurrent. So it generates a photocurrent. It's a reverse current, IP, and you retrieve back the current signal the same 1 0 1. So we have the same 1 0 1 0 0 1 0 1. So what is the point? The point is the last component in this transmitter is a laser diode. It has electronics, it has modulators, and the last component is a laser diode, which is an optoelectronic device. So the laser diode is here, and the first component in the receiver is a photodetector, which is also an optoelectronic device. So you have in between the fiber, laser diode, photodetector, the fiber, and the entire communication electronics here at the receiver, signal processing at the receiver and at the transmitter. So this course primarily deals with the physics, the structure, design of and device characteristics of laser diodes and photodetectors. So this is the relevance in optical fiber communication. But semiconductor optoelectronics is not important only for optical fiber communication, because you know that laser diodes and photodetectors are now used in large number of consumer electronics and the day-to-day devices which we are using, all the laser printers, laser pointers, laptops, LEDs, LED TVs, LCD TVs, everything uses optoelectronic devices. So optoelectronic devices are not, semiconductor optoelectronics is not restricted only to optical fiber communication, but also to a whole technology which involve optoelectronic devices. So I have illustrated this with the example of an optical fiber communication link. One of the earliest optoelectronic devices is the optocoupler. I do not know how many of you have heard about this optocoupler. Optocoupler. This is one of the earliest devices. Optocoupler is a device. Basically, it is a device which had a photodetector here and an LED at the other end. It's a small device which comprised of a photodetector and a light emitting diode. photodetector and a light emitting diode, you have an entire electronic circuitry, a PCB or a circuit board. So here is a circuit board. Which was doing some signal processing operation. There's another circuit board here. You want to link these, but with electrical isolation, complete electrical isolation. So how to do that? You just need an LED here. This is a signal processing board. This is a signal processing board. You would like the two to be linked, but you want complete electrical isolation between these. One of the easiest way was whatever the final output that was coming from here was fed to a light emitting diode. Those days, initial days, only light emitting diodes were used, so LED. This LED light which comes out from here is incident on a photodetector. So this is a photodetector and this is an LED. There's a second photodetector on this circuit. This is just for historic reasons, but it has now come up again in a very big way for high density optical interconnects to connect chips which are dealing with gigabits of data. So this was the early use of an optocoupler which had one photodetector and a light emitting diode. So the signal emitted from this LED is detected by a photodetector, and that current, the current generated by the photodetector modulates another LED which would then couple to this. This is the optocoupler. But you see from here, you don't need this at all. You could as well have the two chips here and the component here, the LED is here and the photodetector is here. So the LED is giving out signals from here and the photodetector detecting it. What is the advantage? The advantage is they are completely electrically isolated. The communication from this to this or the connectivity from this to this is only free space optics. That is free space communication. Today again this was in the early 70s, and today again free space optical communication has become very important, and optocouplers have come in a big way for high density optical interconnects. High density optical interconnects. When you have a computer communication, when computers have to handle very huge amount of data, and if data has to be communicated between two signal processing units, then optocoupler is a very useful interface. But it is not in this simple form. Today, what are called as VCSELs are used. We will discuss about this later. VCSEL. This stands for vertical cavity surface emitting laser. You will study in the course vertical cavity surface emitting laser. You can have very large number of these devices on a single chip, monolithically integrated. But this was the earliest application. But today there are large number of applications, as I mentioned, of large number of consumer electronics goods which use laser diodes and photodetectors. The barcode scanners, which are widely used in marketplaces, it uses a laser diode and a photodetector array to read the barcodes. So let me start with the first question, that is, what is a semiconductor? We all know it, but let me just recall. What is a semiconductor? As the name indicates, it is a semiconductor, which means it must be a class of materials which have conductivity between those of good conductors and bad conductors. Very elementary indeed. Good conductors and bad conductors or insulators. So semiconductors are those which has conductivity in this range. What is the conductivity? So we are talking of conductivity. What kind of numbers? This is a course for engineers. Conductivity. So you have to be familiar with numbers. It is necessary. Large, small do not make any sense. You have to know what kind of numbers, what is the magnitude that we are talking about. So bad conductors, typical conductivity is 10 power minus 12 to 10 power minus 18 Siemens per centimeter. So this is the same as you know, conductivity is inverse of resistivity, and this is basically ohm centimeter inverse. So ohm centimeter inverse, Siemens per centimeter. So bad conductors or insulators typically have conductivity in this range. And what is the conductivity of good conductors? Typically 10 power 4 to 10 power 6 is the conductivity of good conductors, metal. So semiconductors, in general, most of the practical semiconductors which we use have conductivity between 10 power minus 6 and 10 power 3 Siemens. Depending on the doping concentration, as we will see, that the conductivity can be increased. So semiconductors generally have conductivity in this range. Is it sufficient for a material to have conductivity between those of insulators and good conductors and qualify to be a semiconductor? That alone would not have been, if that was the case, such materials would not have had any practical use. Why semiconductors have become so important and so many practical applications are possible? Because the conductivity can be changed by orders of magnitude by the conductivity of semiconductors can be changed by orders of magnitude by doping, temperature, changing the temperature. If you change the temperature, the carrier concentration, and hence the conductivity can be changed by orders of magnitude, and also by illuminating with light, by illumination. By illumination. In fact, the photo detection is illumination of a semiconductor PN junction. Because of these reasons, a semiconductor has become very important because you can change its conductivity by any one of the means or by injection carriers into the medium, suddenly change the conductivity, and these can lead to switching mechanism. So a semiconductor is a material whose conductivity lies between those of good conductors and bad conductors, and whose conductivity can be changed by orders of magnitude by doping or by temperature or by illumination light. There are large number of semiconductors. The most widely used semiconductors in electronics are silicon and germanium. Group 4 elements are most widely used in electronics. But as we will see when we discuss in greater detail, so silicon and germanium are widely used in electronics. They are also used in optoelectronics to realize photodetectors. So these are used to realize photodetectors. But as we will see later, that the materials used to realize light emitting diodes and laser diodes are direct band gap semiconductors such as gallium arsenide and the ternary compounds such as indium gallium arsenide. Indium gallium arsenide, which means in this an X component of gallium is replaced by indium, making it a ternary compound, indium gallium arsenide or aluminum gallium arsenide. Aluminum gallium arsenide. Indium phosphide. Most widely used substrates in optoelectronics are gallium arsenide and indium phosphide. These are binary compounds or binary semiconductors. These are also, as you can see, this is group 4. We will discuss more about this when we discuss semiconductor materials. This is from group 3 and this is from group 5, and therefore these binary compounds are also called as 3,5 semiconductors. So 3,5 semiconductors. We will discuss more of this in the next class, in the next lecture. We will discuss about energy bands in solids and the EK diagram and look at indirect band gap and direct band gap materials. Silicon and germanium are indirect band gap materials and gallium arsenide and indium phosphide are direct band gap materials. As we proceed further, we will see that normally to realize a semiconductor source which emits light, you need to use direct band gap semiconductors. Whereas indirect band gap semiconductors can be used to realize photodetectors. We will basically review the semiconductor device physics to know the density of states, a very important parameter which determines the performance or characteristics of a device is the density of state. So in the next class, we will discuss about density of states. It's a very important parameter, and we will see later on, and when we study the devices, that you will see that the characteristics are determined by the density of state. Okay, so thank you. We'll stop here.